right. So, today we'll continue with roots and weights. And so, last time I think we sort of stopped at the result which said the the angles between roots, right? That was the result. And good. And we gave some examples of these things happening in SU3, but we would look at SU3 in more detail today. So, just to remind you, the angles between roots. So, we also have had some result about angles between roots and weights by looking at the tower. So, remember so this was a general, so if I have some weight level which was mu, then I applied roots, it went to mu plus alpha and so on and so forth. So, the tower had a height of p, and that was the last guy. And it could also go below minus alpha, and it had a depth of q. So, the last fellow was minus this. So, if you really want to be absolutely clear of the notation, then you should also draw another arrow, and that ends at 0. That is to say, the lowering operator acting on this, the last thing here, annihilates it. Okay, and here also the raising operator takes that guy, okay, and annihilates it. Okay, the notation is clear. By this I mean this, that, and then the operator E alpha acting on that stuff annihilates it. And if that is the case, then by sort of chasing the normalization constants at every level and adding them up, we got a master formula, which was which I cannot write up to. So this is the place which I should avoid, right? Good. So the master formula was this. So let me just write it here. That so 2 alpha dot mu divided by alpha square is equal to q minus p. Okay, so q is the depth and p is the height. So this is the master formula which we'll keep using, and q and p are positive integers. So q and p are positive integers. So they belong to z plus. Okay, non-negative integers. So all right, very good, very good. And this we applied to, so you can apply this to any weight system, in particular to root system. Okay, so this is in any representation in which the weight vectors are mu, etc., but you can apply this to the adjoint representation, in which case it will be, the mu will be one of the roots. Okay, so if you start from now, if you start from some beta and keep applying alpha, you will get some beta plus alpha blah blah blah, etc., and going down. So you will terminate at some stage there, and you will terminate at some stage here, and the formula that you will get is that alpha squared is, so the denominator has a norm square of the stuff that is raising you and lowering you. Okay, so it's asymmetric. It's asymmetric between beta and alpha because the roles are also asymmetric. Okay, so you have taken a beta and you are taking it up or down. So this is again q minus p. Okay, this is just a special case of this result. And on the other hand, if you started with alpha and went up and down by beta, then you will get the other condition, which is like 2 alpha dot beta divided by beta square will be equal to some q prime minus p prime. Okay, and this is what gave us the angles between the, so this is some integer, and if you take the same thing with beta squared downstairs, that is another integer, you add them up, you multiply them up, and what you get is, so you have another relation. So this is just to jog your memory. We got another relation here, which was q prime minus p prime. So if you start from alpha and go up in beta, you can get up to some height p prime, let's say, and starting from beta, if you go, alpha, if you go down in using betas, you will have a depth of q prime, and you will get this. So this is an integer, this is an integer, and if you multiply them up, you will get 4 beta square divided by beta square alpha square is equal to integer. Okay, and that's nothing, and therefore you get the relation about. So that was equal to integer by 4. Integer square, excuse me, that was integer square. No, sorry, not integer. Not integer square, it's integer times an integer, so it was that way. So all that you can say from here is that it's integer times integer, that was an integer. So you can say it is integer divided by 4. All right, and for various choices of these integers, so today we are going to sort of get some stronger result about some special subset of roots. These are called simple roots. Okay. And that will turn out to be some very specific angles between. So these guys, if you remember, it spanned all the way from 0 degrees to 180 degrees. Okay, and a whole bunch of angles, 0 degrees, theta, 30 degrees, 45, 60, 90, 120, 135, 150, 180. And but the simple roots, what we will call simple roots, they will have only very restricted possibilities, namely 90, 120, 145, 150, that's it. Okay, so we will see that. Okay, so now let us work out these things in SU3. So for SU3, the weights of the defining representations, so SU3, we did that last time. So they had the structure of some equilateral triangle, and it was half 1 over 2 root 3, and this was minus half 1 over 2 root 3. This was just by looking at the Gell-Mann matrices themselves, or the generators. Okay, and this is something, let me call this mu 1. Well, I'll just call this vector mu 1. This vector is mu 2, and this vector as mu 3. Okay, so this 1, 2, and 3 are labels of which weight it is, and this vector okay, denotes that this is a two-dimensional object with some coordinates in the two-dimensional plane. And just to remind you, this axis denoted the direction x, the x-axis was chosen by h1. Okay, so the eigenvalues of h1 denoted the x coordinate of each of these vectors, and the eigenvalues of h2, so which was t8, and this one was t3 in the Gell-Mann notation. So that's what it is. Now there's a very simple trick to find out what the root vectors are. Okay, namely, just use the fact that the roots, okay, change from one weight to another. Okay, so the difference of this and this must be a root, and the difference of this and this must be a root, and the difference of this and this must be a root. Okay, so how many would you get in that fashion? So from here to here, from here to here, and from here to here, let's say. Suppose you are always going positive. Okay, that's 3 roots. Okay, and the minuses of them, that's another 3 roots. Okay, 6 roots, but in SU3 you have only 6 roots, so that exhausts the possibility. Okay, so let's do the root diagram in that way. So I'll give you the, I'll use this notation that alpha 1 2, okay, is something that is defined by the mu1 minus mu2. Okay, so it's this minus that. Okay, so it's a vector pointing right. Okay, that's my convention. Mu1 minus mu2. These will turn out to be something called positive roots. Okay, so I'll explain, of course. So this mu1 minus mu2, if you do it, you will find that is 1 comma 0. Okay, and then again the thing that takes it to the right is like mu2 3. Okay, so that's alpha 2 3 is this minus that. Okay, so that will be again, so that's like mu3 minus mu2. Can somebody tell me what this is? I'm too lazy to do that.
If 1 2 is mu1 minus mu2, why is 2 3 equal to mu3 minus mu2?
Oh, it should be called 3 2, excuse me. Yeah, so this is half. Oh, maybe my notation is not quite. So I want to do this minus that. Okay, so maybe it should be called alpha 3 2. So then it's half and what? Minus root 3 by 2. Excellent. And the other guy, another fellow, which takes you to the right is this minus that. So that's alpha 3 1. Alpha 3 1, which is this, right? 1 3. Yeah, there's something funny with my notes here. Yeah, alpha 1 3 is correct. Alpha 3 2 is the positive root, is it? Okay, I made some, this alpha 3 2. All right, good.
Should be positive in, for the
Yeah, so that's what I'm looking for, and alpha 1 3 is mu 3 minus mu 1, or mu 1 minus mu 3, mu 1 minus mu 3 is equal to what, half again, and the same thing, root 3 3 by 2. Okay, let's plot these and the minuses of these things. Okay, they will also be, so this we have already proved that day, that if there is there is a root alpha, there is also a root minus alpha. Okay, so the minuses of these things are also so let's plot these things. Okay, so 1 0 is here, and half so let me draw them here, and half and root 3 by 2, it's some stuff here, whatever, and the other guy, it's here. Okay, let me once for all define a notion of positivity. Okay, in these two-dimensional vector spaces. Completely arbitrary notion of positivity. What is the notion of some vector being positive? Is that the first non-zero entry, okay, in the coordinates should be positive. Okay, so for instance, this is something that okay. So let's say positivity of weights. So this guy I would call positive weight because half is positive. Okay, so the first non-zero entry should be positive. This is not positive because the first non-zero entry is negative. So this is positive, this is positive, this is not positive, and this fellow is the first thing is 0. So first non-zero entry is negative, so this is also negative. Okay, so this is positive, this is positive, this is negative, and this is negative. Okay. Now let's look at the roots. In case of the roots, all of these are positive by construction now. Okay, so these guys are positive, and they're what are their negatives? Is that I reflect all of them along the y-axis, and if you oh, sorry, you are right. Around the origin, I have to take the minuses of them. Thank you. So I have to reflect around about the origin. So the minus, if this is alpha, minus alpha is here. Excuse me. Thank you. And like that. And so again, this is H1, this is H2, and sometimes people write 2 dots here just to remind you that in the adjoint representation there are 2 weights which are actually 0. Okay, this we have shown last time, that in the adjoint representation, of course, there has to be 8 weight vectors. Okay, 2 of them will have 0 eigenvalues, and the remaining 6 of them will have non-zero things here. Okay, so these are the positive roots, and these are the negative roots. Okay, so all the roots, all the non-zero roots, they split up between positive and some negatives this way. Okay, we will make a further refinement of in the space of positive roots. Okay, namely simple roots and non-simple roots. Okay, simple roots are positive roots which cannot be written, okay, as a sum of positive roots. Okay, so in this, so I'll write that definition up there soon. But in this diagram, can somebody tell me which roots are simple roots? So let me call this the origin O, and this is something that I would call alpha 1, alpha 2, alpha 3. Okay. So out of alpha 1, alpha 2, and alpha 3, which ones are simple roots and which ones are not? What?
Which cannot be written as a sum of other
Positive roots.
Alpha 3 is not simple.
Alpha 3 is not simple.
Yeah, then alpha 1 and
Alpha 1 and alpha 2. Okay. So, it is indeed true that alpha 1 and alpha 2 cannot be written as, so alpha 1 for example cannot be written as some sum of the alpha 2 and alpha 3, or alpha 2 cannot be written that way, but alpha 3 can be written as alpha 1 and alpha 2. So, the root system actually corresponds to alpha 1, alpha 2 and alpha 1 plus alpha 2. So, this guy is alpha 1 plus alpha 2, and so basically if I tell you the properties, in particular what these vectors alpha 1 and alpha 2 are, okay. In fact, often if I just tell you the angles between alpha 1 and alpha 2, you can construct the entire Lie algebra SU3, okay. So, it is some such thing that we will arrive at the end of today's class.
Sir,
Okay.
Just one question.
Yes.
So, what we call the positive roots are they are dependent on which ones we are calling H2 and H1. Suppose we exchange H1 and H2, and that will change.
Yes,
the definition
indeed,
of our-
indeed, that's correct. So, this ordering, you know, is very arbitrary. It you know, some other choice of H1 and H2 will make, but some ordering is possible, and you can you know, stick to your definition of H1 and H2, okay, in which of course we have used some general general normalization conventions that trace of all these guys, like trace of H1 square, trace of H2 square, trace of this E alpha dagger, E alpha, and stuff like that, all of them are the same, okay, and those same things you can even take that to be 1. So, with these conventions of normalization, you can prove general results about simple roots, and you can construct the the entire you know, root system and the structure constants, okay, unambiguously given an H1 and H2. If you now take that H1 to be T3 and H2 to be T8, then you have particular matrix representation. But otherwise, in terms of some abstract H1 and H2, you have your results. You have generated all of these guys. Okay, all right. So, let me now say that these yeah, so there's an important point here about the SU2 subalgebras sitting inside SU3. So, so you can show the following things. You can show the following things that so I will just write. These are some things which I can probably write here, because never mind. So, let me just write it as a claim, okay, that so I have identified these roots. I have identified these roots, like this is something that I have called alpha 3, this is something that I have called alpha 1, this is alpha 2, and but I have not told you what the corresponding root vectors are, namely what are the generators, okay, which, so this is my alpha 3, but what is okay, that I have not told you. So, what should it do? It should change the eigenvalue of H1 by 1, okay, and the eigenvalue of H2 by 0. That is what it should do, okay. So, from that property you can find out that E alpha 3 is nothing but T1 plus I T2 divided by factorial 2, okay. Let us check it out. So, if you remember what T1, T2, so T1 was something which basically was a J1 sitting here, okay, and zeros in this, and T2 similarly was some 2 sitting here, okay, and T3 was also something which was sitting here, and everything else was 0, okay. And so therefore it's clear, okay, that when I take these combinations, okay, like T plus minus, then it will become J plus minus and J3. So therefore it's clear that, okay, so let me say that this is E plus minus alpha 3 are just these combinations, okay. The claim is that these objects raise the eigenvalue of H1 by 1, but that's clear because T plus minus, so these are something that I am calling T plus minus, T plus minus, T plus minus. So T plus minus and T3, they form an SU2 because they are just sitting here, and the other blocks, they are not doing anything, they are not taking part in the algebra. So this much is clear. I have explained for you this 1. That is to say, when I apply T plus minus on some weight vector, so T plus minus is a raising operator for T3, okay, by an amount 1. T plus is a raising operator for the eigenvalue of T3 by an amount 1. That is just SU2 algebra. Similarly, T minus will do minus 1. 0 I have not explained. That is to say, I have to say that this T plus minus, they commute with H2. But if you remember what H2 was T8, and that had a 1 here, okay, up to some constant, whatever it was, but it had some 1 and it had some stuff here, it has some non-zero stuff here. That was the structure of, it had an identity here, and it had a number outside. So that means that these guys, when you commute, so this T plus minus, even T3, T3 of course commuted with this, that we know, but even T plus minus commutes with this T8. So done. So I have explained the 1 and I have explained the 0. Okay. So this indeed, this T plus minus, the way I have defined them are indeed this positive and negative, the raising and lowering operators corresponding to this root. You can keep doing this, okay, and you can find out that the, in other words, the results are the following, that corresponding to these roots, the raising and lowering operators, the T1, here you have to find out what is the operator which raises the eigenvalues of H1 by half and H2 by minus square root of 3 by 2, and the result is the following, that alpha 1 3, okay, so for this guy it is T4 plus minus I T5 divided by factorial 2, and for this it is T6 plus minus I T7 divided by factorial 2. Okay. So that seems to be a lot of hard work. So let me give you the general trick of how to find these, the corresponding to a particular root, what really are the raising and lowering operators. Okay, so what are these little SU2s, okay, that sits inside some other bigger algebra? Okay, how to find them? So this is the answer. So a general construction of SU2s inside is the following. So, suppose I want to find out the SU2 corresponding to raising and lowering by the root alpha, then I construct E plus minus, that will correspond to J plus minus if you wish, alpha E plus minus alpha, that, and E3 is equal to 1 over alpha square is equal to, sorry, alpha dot H. So, by using the commutation relations that I have already given you, you can find out that the so here what I needed was to find out, well, it does not completely eliminate the work that you have to do, some bit of this work that you have to do, but it helps to know exactly what is the new, so you have only H1 and H2, okay. There are only two Cartan subalgebras, but corresponding to this root, for instance, okay, neither H1 nor H2, okay, is the J3, okay, because both of them are being affected, okay. If these are the J plus and J minus, there should be something sitting here, okay, which would look like 1 comma 0, meaning some combination of the Cartan subalgebra elements H1 and H2, okay, whose eigenvalue is raised here by 1 and here by 0. That formula helps you find these combinations, and that formula is this, okay. What is the particular linear combination of Cartan subalgebra elements which looks like J3 for raising and lowering by alpha? It is this, it is alpha dot H, okay. So, this is like, so now you can show that E plus minus E3 satisfy an SU2 algebra, okay. And in fact, you can get this series, okay, and this beautiful result that alpha dot mu divided by alpha square is equal to Q minus P, pretty much like how you did the SU2. You take this stuff, okay, and you apply, on some weight vector, you apply the E plus up to P and E minus up to Q, okay, and exactly the way you generated the, the 2J plus 1 dimensional representation for SU2, that fact, okay, is exactly equivalent to this one. This is worked out in detail and nicely in Georgia's book, so I am not going to do that for you, but I am just claiming that to be the result. Okay, all right. So, I'll keep this thing here, and I need, of course, okay. So, I'll rub out these parts. I'll leave these diagrams, and I'll work this part. So, now I'll formally introduce the notion of simple roots. Notion of simple roots. I have already introduced to you the notion of positive roots. Okay, by the way, I should also say that if I have introduced a notion of what are positive vectors in a two-dimensional vector space, I have also introduced an ordering, right, because I can say U greater than V if U minus V is positive. That is a triviality. If I know how to define positive vectors, then whether to say that some vector is bigger than another vector, okay, I just compute this u minus v, and if this is positive, then this u is greater than v. Therefore, in a two-dimensional vector space, in a very arbitrary fashion, of course, I can introduce an ordering. Okay. This is not the ordering that we normally use. We can use non-ordering and whatever other things, but this is some thing which you can, not just two-dimensional vector, any dimensional vector space. You just say a positive vector is defined by the positivity of the first non-zero entry. Okay. It's unique, it's arbitrary, but it's unique. Okay. I mean, the definition makes sense. All right. So, what's a simple root? A simple root is the positive root which cannot be written as so as alpha equal to alpha 1 plus alpha 2, where alpha 1, alpha 2 are both positive. So, it's defined through some negative condition, that is, a simple root cannot be written like that. A simple root, a root alpha which can be written like that, alpha 1 plus alpha 2, cannot be a simple root. So, that is a non-simple root. So, therefore, a simple root is something which cannot be expressed in this fashion. Okay, that is the definition of a simple root. Now,
and
yes.
For general Lie algebras, and does this have to be only two of the vectors, alpha 1 or alpha 2, or sum of all the other vectors or something?
If something is writable as alpha 1 plus alpha 2 plus alpha 3, you can group them alpha 2 and alpha 3, that is a positive root. Okay. Sum of two positive roots is a positive roots. So, this definition is enough. Okay. If it is alpha 1 plus alpha 2 plus alpha 3, you can club alpha 1 and alpha 2 together, or alpha 2 and alpha 3 together. It would be a sum of two positive roots. So, so it is enough to rule out this possibility that I cannot find some two positive roots whose sum gives you alpha. Okay. This is a very powerful, surprisingly powerful definition. So, let me give you some results about simple roots. So, theorem 1 is that this is the most powerful thing. So, angle between simple roots is theta is between pi by 2 and pi, and we will say in more detail what these angles are in a moment. Okay. All right. So, there are some sub results that we need. So, there is a lemma that if alpha and beta are simple, then alpha minus beta or beta minus alpha is not a root. Then alpha minus beta is not a root, or beta minus alpha is not a root. Let me call this thing gamma. What is the proof? The proof is the following, that suppose, so proof of this lemma, suppose that gamma is a root. Okay, so this is a proof by contradiction. Suppose gamma is a root. Now, gamma can therefore be either a positive root or a negative root. Okay. Let us say that gamma is positive. let gamma be positive. Then you can take gamma plus beta, that would be alpha. Okay. Now, beta by construction is a positive root, by assumption is a positive root, because it's a simple root, and gamma is a positive root. Okay. So, therefore, we arrive at a contradiction. So, therefore, this possibility that gamma is a positive root is out. Okay, we can't have that. So, this is a contradiction. Let us say gamma is a negative root. That is to say, this is a root, okay, but it is a negative root. In that case, minus gamma is a positive root. So, minus gamma, which is beta minus alpha, is a positive root, of course. And then you can add to this minus gamma thing whatever cancels this one, so plus alpha, okay, that will give you beta. So, then beta, which is a simple root, is the sum of two positive roots, okay. So, that is also a contradiction. So, any which way you arrive at a contradiction. So, therefore, we arrive at the fact that this is true. What does it mean? That means that the simple roots are basically at the bottom of a tower, because you are trying to lower the eigenvalue starting from a simple root. You cannot do it, because if they were not at the bottom of a tower, okay,
Or the top of the tower, right?
no, bottom of a tower.
No, in that case, in that alpha 1 is the top of.
Now, top and bottom have got a meaning, okay, have got an invariant meaning, because when I am saying that I am raising the eigenvalue, okay, that I am making it more positive. Raising has got a meaning now. Otherwise, you could say that, okay, that's convention. What is top and bottom? So, in other words, if I have some alpha like that, I can only go up. I can only go up. So, let us say alpha plus p beta. I definitely cannot go down. If I try to go down, okay, I would have, so if I did that, then there would have been a root which is alpha minus beta, but that cannot be done. So, therefore, I can only annihilate. Okay, so, when I apply the lowering operator, that is to say E minus beta acting on this vector, I must get a 0. Okay. So, by our convention, the depth starting from here I had called q. So, q is 0. Q is 0, and p could be 0 or non-zero, depends on whether there is a vector here or not. Okay. So, p. So, this is something that I got. Okay. So, what does it say for me? That this tells you that alpha, so remember from the general formula here. So, in this general formula, or the formula in the adjoint representation, this was the formula in which I am trying to raise by alpha, then alpha square comes downstairs. Now, I am trying to raise by beta. So, my formula would be in this thing, that it is alpha dot beta divided by beta square has to be q minus p, but now I definitely know for sure that q is 0. Okay. So, therefore, that is minus p. So, I got the very important result that this dot product is negative.
Non-positive.
Non-positive. Okay. So, this and similarly, I could also start with beta and try to raise and lower by alpha. I would have got alpha dot beta divided by alpha square, and that would be some other integer. minus p. Good. So then I can combine these things to arrive at the following things, that so I'll just okay, so these are the two results that I got, okay, that this combination has to be minus an integer and this combination has to be minus whatever non-positive. So this combination has to be a non-positive integer and this combination has to be a non-positive integer, and we will try to construct solutions of these things, okay, in specific situations, okay. Okay, so first of all, so what does it say about the cosine theta? Excuse me, about cosine theta. It says cosine theta has to be negative. Okay, that much is clear. So let me also write down a little bit better. So alpha dot beta. So this combination says it is 2 cos theta alpha beta divided by beta square, that is equal to minus p. So that is that I can cancel out beta thing, okay. So that's one result that I got, and the other one is 2 cos theta beta divided by alpha, that's another integer, some integer, minus p. Okay, maybe this is something that I should mark out as important, and I'll keep it for a while, because this will help us in doing the classification theorem of Lie algebras. All right, so that's what it is, and take any one of these things. It will tell you that cos theta is a negative quantity, and therefore the angle between simple roots is between pi by 2 and pi. Okay, so we have proved this result. So that was theorem 1, and then the here you remember that you got 2 simple roots. Okay, this is not an accident. Okay, the number of simple roots is the same as the rank of a Lie algebra. Okay, so that's what we are going to prove now. Okay, so very quickly I'll prove this. So I will rub this thing off now. So theorem 2 is that, oh gosh. Okay, so I have the general result here. This is the general result. It's also true with mu, alpha dot mu divided by whatever, that thing. All right. Now theorem 2 is that, the number of simple roots is equal to R. That's the rank of the Lie algebra. Okay. So let's see. This proof is slightly long. But let me give you the steps. So I need 2 lemmas for this. Lemma 1 is that simple roots are linearly independent. Okay. So for example, if you have 2 simple roots, okay, then of course they are linearly independent, because some linear combination of alpha and beta is equal to 0, but simple roots are positive, so therefore, okay, so it's for two guys, so alpha and beta, they are of course linearly independent. Why? Because these are positive roots, so therefore one of them has to be positive. Okay, so therefore alpha, let's say it is of this form, y by x beta, but this contradicts that negativity thing. So this is positive. So alpha dot beta will be given by y dot x, y by x times beta square. Okay, that's the positive quantity, but we have found here that the dot product of simple roots has to be a negative quantity. So this is out. You can have 3 of them, let's say, and then it could be some combination this equal to 0. The signs have to flip, because if x and y and z are all positive, then there are sums of positive roots. So positively weighted sums of positive roots, so it cannot be 0. Okay, so it has to be plus minus 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 plus, whatever, something like that. So you write the pluses on one side and the other guys on the other side. Now x, y, and z are all positive. You take dot products, you will find that they are positive. So if you take the dot product with respect to beta, okay, you will or alpha or whatever. So you get x alpha square is equal to y alpha dot beta plus z gamma dot beta. Now these are supposed to be negative by the theorem that we have there. So this is a positive quantity is the sum of negative quantities, so it can't be done. So therefore, we proved that the simple roots are linearly independent. Okay. Now, with this, of course, the simple roots and the number of simple roots can at best be r or less than r. It cannot be more than r, because we are talking about vectors in an r dimensional vector space. Okay, so it cannot be. So this immediately tells us that the number of simple roots has to be less than or equal to r, because in an r dimensional vector space you cannot have r plus 1 number of linearly independent vectors. Okay, so but we want to rule out the possibility that the number of simple roots, for example, could be r minus 1. Okay, it has to be exactly r is what we are after. Okay, to this, unfortunately, I need another lemma, which is an important lemma. So let's do that anyway. This more and more sounds like a math class, but so it's the following: that any positive root, and it has a cool proof, any positive root phi can be written as phi equal to k alpha alpha, where alphas are simple roots and k alpha are positive integers, and k alphas are positive integers. K alphas are positive integers. Okay. This is a rather important result. So let us see how to do this. This proof is so cool that it sounds like it's you are cheated. Okay, so first of all, if phi is a simple root, okay, then this is certainly true, excuse me, that it's a positive linear combination of simple roots, because phi itself is a simple root. Okay. So, if phi is simple, then nothing to prove. Let us say that phi is not simple, phi is not simple, then there has to exist some phi 1 and phi 2 by definition, because phi is non-simple. Therefore, by definition,
Phi is linearly, I mean, the simple roots are linearly independent.
yes,
So, and you said that and if phi is a simple root, then it's and on the other side that's phi itself only, right?
so k alpha
equal to 1 and the rest
1
will be
0
zeros.
1 0 0 0 0 etc. So, there is a,
It's a trivial
for-
case.
it's a trivial case. Let's say now phi is not simple, okay, then there has to exist some positive roots phi 1 and phi 2, okay, which make up phi, right. Now, let us say that if phi 1 and phi 2, okay, are simple, then one is done. If phi 1 and phi 2 are simple, then of course, you know, they are in this list, okay. If phi 1 and phi 2 are not simple, let us say phi let us say phi 1 is not simple, then there will exist phi 3 and phi 4 whose linear combinations these are, and so on and so forth. You recurse it. However, it might go on forever, right, but we are talking about finite dimensional Lie algebras, so the number of roots is finite. So, therefore, this process has to stop somewhere, okay, so you are done, okay. So, we have proved this. So, this is done. This is really a cool proof. Okay. Good. Now, if you have come up to here, and let us say that number of simple roots is r minus 1, something.
But in the recursive process, in the last root is non-simple, it is finite.
You do it again.
But it ends.
It ends. It ends. Why does it end? Because you will keep generating more and more roots, right? But at some stage, you will be you will run out of roots. Why? Because there is a finite number of roots. If there was an infinite number of roots, this proof will not work. Okay. Now, just the last steps in the logic is that let us say the number of simple roots is r minus 1, which is something that we want to exclude, right? So, this is in fact where the simplicity of the Lie algebra will make its appearance. This is one of the places where we are actually going to non-trivially use the fact that it is a simple Lie algebra. Okay, let us see how. We say that the number of simple roots is actually r minus 1. Okay. So, now we can choose some basis in which all simple roots look like the following. Okay, I rub this off. They look like the following. I orient them in such a way that the span of this alpha 1 of all the simple roots, okay, is something for which is avoiding the x axis. Okay. That I can choose my basis in such a way that the simple roots are spanning x2, x3, x4, all the the other n r minus 1 dimensional subspace. So, therefore, all the simple roots are like that. Therefore, all the positive roots also are like this, because the positive roots are all integral linear combinations of these things. Okay. So, all the positive roots are also like that. Therefore, all the negative roots are also like that. Okay. So, all the negative roots are also like that. So, what does it mean? That this means that E alpha 1 commutes with H 1. So, let let me write it in the right order. So remember that H1 E alpha is equal to alpha 1. So let me call these things alpha, beta, etc., etc. So recall that H1 E alpha is alpha 1 E alpha. So that's the first component of the vector alpha. Okay, I have chosen this to be 0. So therefore, this H1 commutes with E alpha. It will also commute with E beta, and it will also commute with everybody else. And it certainly commutes with other elements of the Cartan subalgebra by definition. Therefore, H1 commutes with everything. And of course with itself as well. Okay. So therefore, there is an invariant subalgebra here, which is the non-trivial invariant subalgebra of G. So therefore, there is a non-trivial meaning, I will tell you, non-trivial invariant subalgebra described by H1. Non-trivial meaning that it is not the 0 element, that is of course always an invariant subalgebra, and the total Lie algebra. Okay. Here is something else, this H1, okay, and that we have ruled out because we are dealing with simple Lie algebras now. Simple Lie algebras do not have this. The only invariant subalgebras that they have, okay, are the 0 or the total Lie algebra, full Lie algebra. Okay. Remember what definition of invariant subalgebra is, that it comes when you commute, you take the invariant subalgebra, okay, let us say H belonging to, H in G, take anything in G, commute with H, it comes into H. Okay. So, this is not allowed for simple Lie algebras or even semi-simple Lie algebras, simple or semi-simple Lie algebras, because this is an abelian subalgebra generated just by a single element H1, that we have also precluded by defining semi-simplicity to be more than simple, but it's something which is not allowed to have a U1 subalgebra. Okay. So therefore, by using this fact now, we can. So this is one of the places where we are using it non-trivially. So therefore, the number of simple roots cannot be r minus 1, and similarly, of course, the if you do the r minus 2, then you can do the same drill here. That much is clear. Okay. So therefore, the number of simple roots must be r. So we are done. Number of simple roots is r. Okay. I'll drop this off. So we are progressing gradually. Now, so after this, there is a little kind of slightly longish. I'll skip that part. Okay. So how, starting from the point is that, okay, let us see what is the general game now, is that in order to, so this is the claim, that in order to specify all the roots of a Lie algebra, all we have to do is to specify all the simple roots, okay, and more or less only the angles between each pair. Okay. then we are more or less done. Only more or less, because I cannot quite say as yet that all of them, all of the simple roots have the same length. Okay. So, but first of all, this much is clear, that if I have given you the really all the simple root vectors, then you can construct all the roots. Okay. How does that go? Okay. That I have not told you. All I have told you is this theorem, not this one. Okay. That positive roots are some positive integral linear combination of simple roots, but which ones? Okay. So, we will do our tower business, okay, and see where we go. Okay. So, there is a general discussion of this which is done nicely in Georgia's book, but let us do this for SU3. Okay. So, in SU3, so somebody has told you that in SU3 these are, okay, so I am probably not keeping my notation for which one was alpha 1 and which one was alpha 2 like before, but right now I will say that so let us also note down some facts here. So, suppose somebody has really given you the root vectors themselves, the simple root vectors themselves. Okay. I want to find out now how many of these things, alpha 1 plus 2 alpha 2 or alpha 2 plus 2 alpha 1, you know, and what are out of all these possibilities, enormous number of possibilities of integral linear combination of alpha 1 and alpha 2, which one of these are really roots? Okay. It has become a problem of geometry now. You can see I am not doing any commutation, anybody, anything, you know, that's all gone somewhere else. Okay. And that's the game that is played, you know, in this classification thing, and much of Lie algebra theory and even in representations. Eventually, it becomes some, you know, geometry of vectors in an R dimensional space. Okay. Have I talked about any commutation relation at all in today's lecture? No. Okay. So, let us try to find out whether alpha 1 plus alpha 2. So, first of all, you know, so you know this thing called a lattice, right. So, what you do is to draw some alpha 1 and alpha 2 and draw a lattice. This thing is called a root lattice.
We allow for negative integers as well. I mean,
so, the negative roots will be some negative stuff. So, all the roots, okay, the non-simple roots will be some points here, but how far can we go? How far should we go? Of course, we should not go very far because the number of roots that we need, okay, is finite. Okay. In this case, we need only one, okay. But we can rule out, okay, starting from this fact that there alpha 1 and alpha 2 are two roots, okay, we can find out that you know, alpha 1 plus alpha 2 is the only other positive root that can be there. Okay. In fact, do not think that if alpha 1 and alpha 2 are only the two roots, then alpha 1 plus alpha 2 is the only possibility. There is some strange group called G2, some Lie algebra, for which there are many more roots. There are only two simple roots, rank is 2, okay. But there are lots and lots of, not lots and lots, I mean some several more. So, we will do the G2 analysis also today if we have time. Okay, so let's go. Let's see. So, I want to rule this thing in, rule these things out. Let's see how that goes. Okay, by now probably you know the game that I'm going to play. So I start from alpha 1. I start from alpha 1. And I try going up a number of times and see how far I can go. Okay. The last chap I go to would be alpha 1 plus p alpha 2, right? And I also know that I should hit a 0 here, and of course by definition I should hit a 0 here. Okay. So I want to determine p basically. But p is given by the dot products of alpha 1 and alpha 2. Okay, no big deal. So I have already written something here. So I just apply these formulas. So in this way, so remember the formula is that the stuff that appears downstairs is the operator that takes you around. So that's alpha 2 square, and that should be my minus p. Let's work it out. What is this? Can somebody tell me? P is 1. So everybody got this thing to be minus 1. This is minus p, so p is 1. So the tower has height 1. So therefore I must stop here, okay, and 0 here. So therefore alpha 1 plus 2 alpha 2, that is ruled out. But alpha 2 plus 2 alpha 1 is not ruled out that way. Let's do that also. So for that I start from, I have to switch the role of alpha 1 alpha 2, this is alpha 1 square, and in this it turns out that all the alphas, okay, both the simple roots have mod square equal to 1. Okay. So this is supposed to be my other integer p prime, which is the height of the other tower starting from alpha 2, the height of this tower, but the height of this tower is also equal to 1. So therefore this possibility is also out. Therefore the only point in the root lattice is alpha 1 plus alpha 2, that is the other root. Okay. Of course, as soon as somebody has shown me that alpha 1 plus alpha 2 is an allowed root, I have exhausted my positive roots anyway, so I do not have to go any further. But if you wish, I could have done this way to prove that p is equal to 1, and that is the most that you can go, and p prime is also equal to 1. So you could actually rule these things out by the angles that you have. Okay. For example, if somebody has given you some simple roots and you do not know the total dimensionality, you know the rank is 2, but you do not know the dimensionality of that Lie algebra. You do not know when you are exhausted. For example, G2 is some strange Lie algebra for which the rank is 2, but the dimension you do not know, let us say. Okay. But the vectors are different. These vectors are different. But by looking at these vectors, okay, you can be you can find out how much you can go up in alpha 2 and how much you can go up in alpha 1, and you can actually find out. Let's do that exercise. Okay. That's an interesting exercise to do. Let us see before that whether I had something. All right. Let me see. So I'll do that exercise now. But before that, just in case I miss the punchline of today's thing, so that is the Dynkin diagram representation of Lie algebras. So let me just say what that is. So, it is the following that so this is the Dynkin diagrams these are basically shorthand representation of the set of simple roots. Okay. In this I need the following. So, roots are defined by these circles. Okay. These white circles are roots. Okay. And if the angle between two roots is theta equal to 150 degrees, that is to say this object is minus root 3 by 2, then it's a triple bond. Now we are doing chemistry from exotic mathematics to exotic. No, this is not exotic chemistry. Everybody knows about double bonds and triple bonds. So, this angle, which is basically 90 plus 45, so that is a double bond. This is 120, which is the angle is equal to minus half, and disconnected blobs, that is 90. Now, if if all the roots had the same length, okay, and I can always choose the length that length to be 1, let us say, then specifying angles between roots is the same as specifying the roots. Why? Because I could start from the first root, okay, as something, my x-axis, okay, let us say the unit vector on the x-axis, and then I can construct all the other guys by geometric constructions, okay, because I know the pairwise angles, okay, simple roots. And then from then on I can construct the positive roots. By the way, I have explained, because I know the angles, I know the heights of towers starting from simple roots, okay. And after I have reached a positive root and I want to apply some raising and lowering operators from there, that also I can do. I'll have some depth as well from there, but I have kept track. I have started from some simple root always, okay. So, how many raising operators I have applied in some direction. So, these I am just saying this requires some explicit working out of examples. So, let us see. So, let me first claim now that the various Lie algebras, okay, like SUN plus 1 is given by, so now watch what I am doing. All single bonds and n blobs. This is given the name AN. Okay. So, this is the representation of SUN plus 1. Okay. So, for SU2 is just a single blob. There is one simple root, okay, which I can conventionally call alpha. okay, and there is that also is the only root, which is the positive root, okay, because you know there is no other route to take integral linear combinations to generate something else. So of course there is a negative root, so alpha minus 1, so these are all roots alpha and minus alpha. So single blob means that, and of course there is only one Kato subalgebra element, that's H1, okay, and clearly it's generating an SU2 thing, that's for sure, because H1 acting on thing is that vector E alpha, and plus minus alpha is equal to plus minus that. And remember that we also have this result, which you may have forgotten by now, which is that this is equal to alpha dot H, but alpha is now a zero dimensional vector, so it's alpha H1, and this is all that. So just from the fact that this SU2 is a single blob, we have generated the SU2 algebra. Let's do the same thing for SU3, which is a slightly more non-trivial, of course. So for SU3, what does this rule say? It says that I should put n equal to 2. Okay. So first of all, I should explain that SUn plus 1 has rank n. Why? Or SUn has rank n minus 1. Can somebody explain that? Exactly. So for SU4, for instance, you can have 1 minus 1 0 0, or shift the 1 minus 1 across, okay, you will get 3 of them. Okay. So you can have at most 3 commuting generators, so rank is 3. Okay. The counting is slightly more involved for SO groups and SP groups and so on and so forth, but for SU it's easy. Okay. For SO also is not such a big deal. I mean, it's like commuting planes, find out the non-overlapping planes of rotation. Okay. So, sorry? Huh? Floor function event. Oh yeah. So people write the SO2n and SO2n plus 1, you know, separately because of that, so that the floor functions don't enter. Right. Good. So now let me write. Okay. So SU3. Can somebody dictate to me from here what SU3 should look like? So it's like 2 blobs with a single bond. Okay. So 2 blobs with a single bond. What does it say? It says that, let me call these things alpha and beta. So it says that alpha dot beta is equal to minus half. Minus half. Okay. Now I can use these facts that so 2 cos theta alpha over beta is equal to minus p, and 2 cos theta beta over alpha. This was true for any pair of simple roots, but I have only two simple roots here, which I have called alpha and beta. So this has to be true, minus p prime. Now if you multiply this out, okay, what will you get? So first of all, from here itself, so remember this was cos theta. So what do you get? That cos theta is equal to, so 2 cos theta is minus 1. So alpha over beta is equal to p. So that's an integer. okay, and from the other one you will get beta over alpha equal to p prime, that is also an integer. How is that possible? Both are equal to, they both are equal. So therefore I get right away that from the fact that alpha dot beta, this alpha hat dot beta hat is minus half, that is enough for me to specify what the things are. So in fact then you can choose alpha and beta themselves to be 1, but let me not even say that much, you know. Let us say, so what I got is beta is equal to alpha. Now you can just do this analysis of, so does it tell you about what the vectors themselves are? Okay, they do, okay, up to some rotation. Okay. You can choose your alpha to be some, okay, so let me choose equal to 1. This is you know, without loss of generality, but you can put some arbitrary number lambda here, okay, and you can do your analysis like that. Okay, so this is equal to 1, therefore you can choose alpha to be this way, okay, and you can choose beta to be this way. Remember the angle has to be 120 degrees. And from this fact alone, you can find that alpha plus beta is the only possibility. Alpha plus 2 beta will not do. Beta plus 2 alpha will not do. That exercise we have already done. Okay, so what does it mean? That means that I can take alpha to be 1, 0, okay, and beta to be whatever it is needed to be. So alpha to be 1, 0, and beta, what should beta be?
Minus half root 3 by 2.
Minus half root 3 by 2. So I have actually constructed what alpha and beta are. Of course, the more conventional thing is that you can take alpha and beta to be at 60 degrees with the x-axis. That is Gell-Mann's convention. That need not be my convention. Okay, so you can take that. Oh gosh. Oh. Okay. So you can choose your basis of Cartan subalgebra in such a way that in such a way that, so this is some 60 and this is some 60, so that my 60s are not very good. So this is alpha and this is beta and this is 60 and this is 60. Okay, and that's Gell-Mann's convention. So therefore you have, okay, Pranjal has appeared, so which means that my time is up. Okay, so let me just tell you that with two blobs, okay, there is another possibility, which is the following. Okay, alpha and beta, and alpha dot beta is equal to, the triple bond is minus
But this
root
is
3
no
by
longer
2.
SU3.
What?
But this is no longer SU3.
This is no longer SU3, exactly. So, oh, by the way, let me complete this story. So, I have constructed alpha and beta exactly. So, this will give you Gell-Mann's convention, but merely a convention again. So, alpha is half root 3 by 2 and beta is equal to half minus root 3 by 2, and the rest of the story is, you know, the alpha plus beta is the only other root, blah blah blah. So I have got all the positive roots, all the simple roots. Oh, I forgot to say that of course the same angle business also gives you the E alpha E beta commutation relations. Okay, shall I while you know the E alpha E beta commutation, what is this? So I start from here, I go to alpha plus beta. When I'm going from alpha to alpha plus beta, I generate a normalization condition. That normalization condition is nothing but the following thing, right? So this is saying that E beta, so what I'm doing here, this is in the adjoint representation. This is the fun thing about adjoint representation. I am applying this, okay, and this will give me something proportional to E beta plus A alpha plus beta. But this is nothing but a commutation relation, because this action is a commutation action, this is adjoint representation. And this is something that we had called N beta alpha, and those were given by the dot products of alpha and beta, correct? Everybody agrees with me? So therefore this stuff N beta alpha is something that is known, E alpha plus beta. So therefore, given the simple roots, the structure constants of the commutation between simple roots is known, but all positive roots are known linear. I mean, we'll find out what those linear combinations are out of the root lattice, which integral points correspond to positive roots, okay, that we construct, okay, by finding out these p's and q's. Therefore, the commutation between all the positive roots and all the negative roots are also known, okay. By some conventions we can make them better and better and better, we can be clever about conventions, but as soon as our simple roots are known, okay, we got the structure constants, all the structure constants as well, okay. Now, okay, so I'll do this stuff tomorrow, next time, that this animal is called G2, and if there is a triple bond, the lengths of alpha and beta have to be different, okay. And we'll also talk about the Dynkin diagrams for other Lie algebras. Next time we'll start on representations of the Lie algebras.